Hello everyone, in this video we are going to look at a batch reactor that has a first order reaction going inside. We're going to think of that as A goes to B. A is some chemical species that converts into B in this reactor. And our goal is to figure out how does this reaction proceed with time. And so we're going to calculate our number of moles of A as a function of time, figure out what this differential equation is, and we're also going to use a concept called conversion. And we're going to write that as x in dx dt. This conversion is basically how much of A has been converted into B over the course of time. It goes from a value of 0 to 1. And we're going to look at these two differential equations. We're going to solve them and then figure out how long we have to wait for a certain amount of A to be converted into B. So that's the goal of this problem. We're going to assume that we have a constant volume, which is pretty common. If we have a batch reactor, it's often an enclosed vessel that can't expand in volume. We'll also assume this is constant temperature. Things get more complicated as we can change the temperature. We're also going to assume this is a well-mixed vessel. You can imagine if this wasn't well-mixed, you might have a different amount of reaction proceeding at the bottom compared to the top, and we want to avoid that situation. So the steps to solve this problem: first, we're going to set up a mole balance on species A. Then we're going to rewrite the mole balance in terms of the conversion x. And third, we're going to solve the equation. So our mole balance is going to be d Na dt. So figuring out how does the number of moles of A change as a function of time. And in general, for these reactor problems, that's going to be equal to how much of A comes into the reactor minus how much goes out, plus some term that we're going to call generation. So this is basically all the components that are reacting within the system. And this generation term, we're going to think of it as a positive if it is being created, and it's negative if it is being consumed. So since we're in a batch reactor, we don't have anything coming in or out of this reactor. So these two terms are equal to 0, and we're left with our generation term. So our generation term can be written as our rate of reaction, which is going to be called RA, rate of reaction of species A, times the volume of our reactor. So this rate of reaction is in moles per time per volume, and if we multiply that by the volume of the reactor, we get to the units of moles per time over here on the left-hand side of the equation. Now, since we have a first order reaction for this problem, our R sub A is equal to minus K times the concentration of A. So this K is our rate constant, and this is a negative sign here because A is being consumed within the reaction. So we can rewrite our differential equation right here as dNA dt is equal to minus KCA times the volume of the reactor. And you'll notice this is a negative sign. That means that our differential equation here is going to be decreasing with time. One way we can rewrite this to solve this immediately without getting into conversion is to move the volume to the other side of the equation. So we get 1 over V times dNA dt is equal to minus KCA. And since our volume isn't changing with time, our volume is constant, we can pull this inside of the derivative symbol and we get the number of moles per volume, which is just our concentration. So then this becomes dCA dt is equal to negative KCA. And this is a differential equation that we can solve. So we can solve this right here in terms of our concentration, come up with our concentration as a function of time. But for this problem, we're going to try to rewrite this in terms of conversion, which is a dimensionless quantity, and see how we can solve that problem. And you'll find out that the two solutions end up being exactly the same, but just written in terms of different variables. So returning to our steps, we have set up a mole balance. The next step is to write this mole balance in terms of the conversion x. So first off, what is x? So x is the conversion. It's defined as the number of moles reacted, moles of A reacted, divided by the number of moles of A fed to the reactor. So that's the number of moles at the initial time point. So we can write that as, let's say, Na is the number of moles in the reactor at time t. So at some point in time t, right, a number of moles of A, it does change with time. We're going to define Na0 as the moles of A at the starting point. And so then we need to figure out how many moles of A have reacted. That's the numerator of this equation. So that's going to be Na naught minus Na. So the total number of moles that have reacted over the first t minutes or t hours will be this difference here. So our conversion then will be equal to this term divided by, again, the moles of A fed to the reactor, which is just Na0. And we can also write this by solving for number of moles, Na. So let's multiply by Na0 and then subtract by Na naught. We end up by solving for Na, we can get Na is equal to Na0 times 1 minus x, 1 minus the conversion. So both of these two terms will be useful when we try to figure out how do we put the conversion into our differential equations. So our previous differential equation we have here, we have this in terms of the concentration of A. We can also write conversion in terms of the concentration. All we need to do is divide both sides of this equation here by the volume. So if we take left-hand side of the divided by volume, right-hand side divided by volume, this Na divided by volume is just our concentration. And again, over here, Na naught over V is also our concentration at the initial point. So we can rewrite this as Ca is equal to Ca naught times 1 minus x. And so here's another way of looking at that same equation. So the next step now is to rewrite this differential equation we have right here in terms of our conversion. First, let's plug in Ca into the left-hand side of this equation. So we're going to take the derivative, so d dt of Ca0 times 1 minus x. And since Ca0 doesn't depend on t, of course, we can pull that out of the derivative, and then we can just take this derivative of 1 minus x. So that gives us Ca0. X does depend on t, so we have to take this derivative. And since there's a minus sign here, we'll pull that out. And of course, this 1 goes away in that derivative. For the right-hand side of the equation, we'll plug this in here and just make sure we keep track of the minus sign. So we get minus kCa is equal to minus k Ca naught times 1 minus x. And now we can plug these two equations together. So we get left-hand side minus Ca naught dx dt is equal to minus k Ca naught 1 minus x. And these concentration terms will cancel out. The minus signs will also cancel out. So we're left with dx dt is equal to k times 1 minus x. To solve this differential equation, let's bring the x terms over to the left and then move t to the right-hand side of the equation. So we get dx divided by 1 minus x on the left is equal to k dt. Here's where we're going to take the integral. So we're going to integrate on the left-hand side from 0 to some value x. And on the right-hand side, we're going to integrate from 0 to t. So this is basically going to tell us at time t, which could be some arbitrary time, what is the conversion after that point. So the right-hand side is a nice easy integral. So I'm going to do that one first. This is just equal to k times t. Left-hand side, you'll probably remember that this bottom part, if you have a 1 over x, this will turn into a log. So will become natural log of 1 minus x. But then remember, we have a minus sign because we're subtracting x, so we'll take a minus sign over here. And we're integrating this from 0 to x. And this is equal to negative ln of 1 minus x, because the natural log of 1 is equal to 0. Now we can move this negative sign inside of the log just for a little convenience. That becomes ln of 1 over 1 minus x. And then now all we have to do is combine these two parts of the equation right here and here. So we end up with kt is equal to natural log of 1 over 1 minus x. And this will describe our system. One common thing that you might want to do to characterize this reactor is figure out at a desired conversion, how long does it take to reach that conversion? So for example, maybe you want to let the reactor go until A is converted to B by about 90%. So 90% of A has been converted to B. Then what time will that take? So to do that, we can solve this equation for time. So we get T is equal to 1 over K times the natural log of 1 over 1 minus x. And that is our solution to this problem. So coming back to the original problem setup, again, we have a batch reactor going from A to B. And what we did is we set up a mole balance in terms of dNA dt. Then we converted that mole balance into conversion. So we have a differential equation of x, where again, x is the conversion. It goes from 0 at the starting point of the reaction when there's been no reaction has taken place. And it goes to 1 when this reaction has fully converted from A to B. And then finally, we solved that equation and ended up with this solution right here. I hope you enjoyed this video. Thanks for watching.